5.3 is graphs of rational functions of the form ax plus b divided by cx plus d. So what's that mean? The number one thing to take from this form is that the degree of the x's are the same. And there could be a coefficient in front of the x's. I mean, if there's not, it's just a 1. And there's an addition of some sort of constant, or it could be a subtraction, an addition of a negative, whatever you want to look at. Now, how do we graph these things? There are certain properties we need to know in order to graph when we're graphing. We want to know the domain, the intercepts, the asymptotes, the positive, negative intervals, and lastly, the intervals of increase and decrease. If we know all these things, it's pretty easy to translate it into a graph, and I'm going to show you some quick skills in order to extract these pieces of information and then graph. So let's take a look at the first one. Our first example is x minus 2 divided by 3x plus 4. Let's take a look at the domain for a sec. Our domain for this function is x is an element of all real numbers. But what do we know about x? Right here. It can't be negative 4 over 3. Remember, it's always opposite this over this. X cannot be negative 4 over 3. We know how to do that already. I'm not going to get into making this equal 0, but if the denominator is 0, this can't exist, which makes this our domain. So now I know I have a vertical asymptote at negative 4 over 3. At negative 4 over 3, I have a vertical asymptote. I know that my graph cannot touch that dotted line. Awesome. That's a very important piece of information. Next, intercepts. Intercepts. First of all, my y-intercept. My y-intercept is always pretty easy. All I have to do is plug in 0. If I plug in 0 into the function of x, I'll get my y-intercept. This is 0, this is 0. My y-intercept is negative 1/2. So I plug in 0 and I get negative 1/2. Negative 1/2 is my y-intercept, so I plot that point. Let's do the x-intercept. The x-intercept is always more difficult than the y-intercept. When you're looking for x-intercepts of rational functions, look at the numerator. Because when the numerator is 0, this is when the function will be 0, and this is your x-intercept. It has nothing to do with the denominator, just the numerator. And that's it. Okay, so when is it going to be 0? 2. So at 2, 0, we have an intercept. Plot it. 2, 0. Next, asymptote. Done. I already figured out my asymptote by doing my domain. I already plotted it. Those are 3 properties already taken care of. Now, positive and negative intervals. Where am I graphing this function? Is it below the x-axis or above the x-axis? Just looking at these 2 points, I kind of have an idea on where it's going to be. Okay, oh, actually, sorry, we're missing one asymptote. So asymptotes is x equals negative 4 over 3. That's the dotted line, the equation of the dotted line. But we also need that horizontal asymptote. Where is my horizontal asymptote in this case? Big miss. Okay, remember from 5.2's lesson, when the degrees of the x's are the same, you need to look at the coefficients. So the horizontal asymptote, as x approaches infinity, is going to be 1 infinity over 3 infinities, which is really 1 over 3. So at 1 over 3 here, I have a horizontal asymptote. All right, now we're moving on to positive and negative intervals. Positive and negative intervals. Very important for the rest of the chapter because this is going to help us solve inequalities. So, what I like to do for positive and negative intervals, I like to make a quick graph. Now, how do I make a quick graph? So positive and negative intervals, the same way I always have made a graph. I plot all my important points, which is my asymptotes in this case, and my intercepts. So everything that has to do with x, I plot. Now we used to graph like this, right? So negative 4 over 3. Oh, sorry, that's supposed to be negative 4 over 3. Take that in. You guys thought I wouldn't catch that, eh? Already trying to write some comments. Okay, so negative 4 over 3, positive 2. on this graph, this is not a graph of the function at all. It has nothing to do with the function. This is just how we're going to determine the positive and negative intervals. So I plot my vertical asymptote and my x-intercepts, everything that crosses the x-axis. And now I look at the function and I count the same way as polynomial functions. How many degrees is that in total? That's 2 degrees. It's positive. This really would look like a parabola. Even though it does not look like a parabola, this is just a way to determine the positive and negative intervals. Now it's really clear from this graph that this function is negative between -4 and -4/3 and 2, and it's positive here and positive here. Well, the same thing is going to be true here, which means I'm going to graph here, and then I'm going to graph here, and then I'm going to graph here. Okay, so this is what this means. I can split this into 6 sections, and it'll help me understand where I'm going to graph. The where is very important. So, how do I figure out what to graph, up here? You can plug in a point if you want, okay, but it's usually going to kind of look like this. Okay, what's going to happen over here? And it's going to approach the asymptote. Okay, and there was nothing over here. I don't know why I said that. This is just going to slowly approach 1/3 and never touch it. Okay, now, the intervals of increase and decrease is something that's going to be separate, but you also need to know. So an interval of increase and decrease in this function, this is obviously increasing, this side, right? This one, I don't know why, but some people think this is decreasing because it's increasing at a smaller rate as you go forward. So people think decreasing. Okay, it's not decreasing, this is still going up. So this function is actually increasing XER. From the beginning, -infinity to infinity, this function is increasing. You do have to omit -4/3 though, because nothing is happening at -4/3, so you can't really say it. So I'm going to say that function is positive. So I'm going to use interval notation for the positive negative intervals and the intervals of increase and decrease. So it's positive from -infinity to -4/3, and it's negative from -4/3 to infinity. Like you set notation, interval notation, whatever you want. Now, it's increasing from -infinity to -4/3, -4/3 to infinity. So this is how I omit the -4/3. I have 2 different intervals, and it's decreasing never. And that's it. Everything is kind of already known from chapter 4 over here. The main idea here is this. It's the easiest way to find positive and negative intervals. It has nothing to do with the graph of this function, but it'll tell us when it's above 0 and below 0 and help us understand where we're going to graph this thing. Okay, so now for this next question, f at x equals x minus 3 divided by 2x minus 6. We're going to try to use the same principle. However, we're going to try to bail out of this question or see when we can bail out of a question as early as possible. And that usually happens when there are holes in questions. Now, you should notice here immediately that these 2 numbers are even, so I can factor out a 2. So I can reduce this or simplify this to 2x minus 3. So I factored the denominator, and now it's obvious that I have a hole. So when x equals 3, I have 0/0, therefore I have a hole. But look what happens here. I can kind of simplify this, right? These cancel out. These are factors. This just equals 1/2. So this function and this function are the same. 1/2 is just a horizontal line. Horizontal line at 1/2. That's a grade 9 question. What's the only difference here? Well, you have to consider the restrictions everywhere. Well, there's a hole at 3. So at x equals 3, you have a hole, which means the function can't exist there. Can't exist there. And that's it. I've already graphed it. So there are going to be situations where you can simplify it into a linear relation and graph it. And just, grade 9, and there's that grade 12 piece right there. Put that hole because the function can't exist there. Do I have any asymptotes here? You may think 3, or positive 6 over 2, which is 3. But unless you simplify it, you won't be able to see that the fact is you don't have a vertical asymptote. You don't have a horizontal asymptote. You want to talk about intervals of increase and decrease? This is not decreasing or increasing anywhere. This is positive everywhere. So all these answers are pretty obvious once you graph a simple line. Okay, so yes, these are the properties. We love looking at them. They help us graph complicated questions. But sometimes something that looks similar complication can be done very, very quickly. So we want to find those out anytime we can in this section especially.